The Fischer esterification is an important reaction in organic synthesis because it allows transforming carboxylic acids into esters. That's when carboxylic acids are treated with an alcohol in the presence of an acid catalyst. Let's draw a general scheme for this reaction, and then we'll see how we can work out a possible mechanism for the Fischer esterification reaction. So this is the general scheme. We take a carboxylic acid whose general structure is of this type. Carboxylic acid is treated with an alcohol whose general structure is ROH in the presence of catalytic acid, something like HA in general, something like that. And then we get the corresponding ester. And of course, remember, esters are derivatives of carboxylic acids. Therefore, they undergo nucleophilic acyl substitution reactions, amongst other reactions, of course. Yeah. Now, let's see how we can work out a mechanism for this reaction. Now, this catalytic acid is very important. The acid catalyst is very important in this reaction. The first step would be then protonation of the carboxylic acid. A good question would be, which of these oxygens is more basic? In other words, which of these oxygen gets protonated? Is it this oxygen of the carbonyl group or this oxygen? It's actually that oxygen that is more Lewis basic, and therefore it gets protonated. That's because the corresponding conjugate acid is stabilized by resonance. So let's work out the first step, and then we see what we can do from there on. So these are the two lone pairs on that oxygen, and this is the HA, the acid catalyst. So this oxygen picks up a proton from the acid catalyst. So oxygen makes a bond with hydrogen. Of course, the HA bond breaks simultaneously. It is protonation. So let's draw the conjugate acid of this protonation step. So this is the conjugate acid. Now, we can clearly stabilize this by resonance using one of the lone pairs on this oxygen. Now, if this oxygen, for example, gets protonated, stabilizing the corresponding conjugate acid, which results after protonation of this oxygen, would not be stabilized by resonance. Now, this suggests that that oxygen is actually more Lewis basic, because this conjugate acid again is actually stabilized by resonance. If we use one of the lone pairs on this oxygen, so we take one of the lone pairs, we make a double bond here, and then this carbon-oxygen bond gets broken, releasing electrons to that positively charged oxygen. So let's draw the resonance form. So this is the resonance form. So this is an evidence, if you like, of the higher or relative higher basicity or Lewis basicity of that oxygen, relative, of course, to that oxygen. So that's exactly why carboxylic acids are actually basic on that oxygen, but not on this oxygen. Now, this intermediate is actually electrophilic. It can undergo nucleophilic addition type on this carbon, and the nucleophile is now the alcohol. Of course, alcohols are neutral nucleophiles, but with this highly electrophilic intermediate, they can do the nucleophilic addition despite their neutral nucleophilicity. So the alcohol now will come in. So this is the alcohol of this general structure. Alcohol will now come in and attacks that carbon, and then the carbon-oxygen bond is broken. So something like that. So it's nucleophilic addition type, and then the product would be this intermediate. Now, after this, that intermediate would lose a proton to a conjugate base or to a base. And of course, if you look at the mechanism at the beginning, okay, there is A minus, the conjugate base of the acid catalyst. Now A minus will come in and take off that proton from this intermediate. So A minus here will come in and take off this hydrogen, breaking the hydrogen-oxygen bond and releasing, of course, electrons to the positively charged oxygen. So the intermediate then, after this, would be this one. And this intermediate is actually neutral. Now at this stage, one of the hydroxyl groups should be lost because in the S, of course, there's OR prime, which we already have. So one of the OH groups here should be lost. Of course, the OH minus, or the hydroxide ion, is actually a poor leaving group. It can only leave if it gets protonated. So that's an excellent way to make the OH a good leaving group, which is water. So protonation is then required on this tetrahedral intermediate, and the protonation would be using the acid catalyst, which has been just reformed. Okay, the acid has been reformed, so which is used to protonate this tetrahedral intermediate. So this oxygen then would be protonated using this catalytic acid that has just been reformed. So we take an arrow from that oxygen to that hydrogen of the HA acid, or the catalytic acid, and the HA bond, of course, breaks simultaneously, releasing electrons to A. So what we get is the following. This intermediate is actually then formed. So now OH2, or water, is an excellent group. So this protonation, okay, is very important because it sets the stage for the departure of OH in the form, of course, of water, which is an excellent leaving group. So this OH2, or water, is actually ready to go. And we can use one of the lone pairs on this oxygen to expel it. So we take one of the lone pairs on this oxygen, and then we make a double bond here. And of course, this H2O now leaves, it departs, because now it is an excellent leaving group again as a result of this essential protonation step. What we get now is this intermediate. Now, if you look at this intermediate, we have most of the components. Okay, so we are nearly there. So the last step would be actually for this intermediate to lose this hydrogen, and what can come in now is actually a conjugate base. So A minus, the conjugate base of the acid, which was used in that protonation step. So the A minus can come in now here, the conjugate base of the acid. Remember, if it's HCl, then it's Cl minus. If it is sulfuric acid that was used as an acid, then it is the hydrogen sulfate ion that acts as a base in this step, and in all of these steps which require deprotonation by a conjugate base. So the conjugate base then comes in, it takes off that proton, and the hydrogen-oxygen bond is broken, releasing electrons to that positively charged oxygen, furnishing the last, or the final ester product, which is obviously the one that also appears in the general scheme. So that's the ester product. So this is a very interesting reaction, the Fischer esterification reaction, because again it allows transforming a carboxylic acid into an ester, an ester by treating the carboxylic acid with an alcohol in the presence of a catalytic acid. Remember, the initial step is protonation, and it is that oxygen, again, that gets protonated, not this oxygen. That's because this conjugate acid is stabilized by resonance as shown. And the mechanism takes a usual course, basically. And remember, it's a catalytic acid, so it is used initially, but then obviously it should be reformed for it to be reused. And thus this character of a catalyst. A catalyst, remember, is a substance that's used and reused but never consumed. So it is used, reformed, and reused all the time. And even here, in the final deprotonation step, the acid catalyst is also reformed because it allows its reuse or recycle, if you like. We can actually write it also. So it's plus HA, the acid catalyst, because it's using catalytic amount. So in summary, the Fischer esterification reaction is an important reaction for transforming carboxylic acids into esters by treating or by reacting the carboxylic acid with an alcohol in the presence of an acid catalyst.